So let's talk about mean parametrization and inference problems, which is really important. So it turns out that any exponential family has an alternative parametrization in terms of vector of mean parameters. So instead of working with theta that I showed you in the previous lecture, we want to work with a new parametrization, which is with mu. And various statistical computations among the marginalization and maximum likelihood estimation can be understood as transforming from one parametrization to the other. So when we use this parametrization, we can understand and solve many intractable, let's say, models. So the idea is very simple. We just take the expectation of that p of x, which is really hard. We take the expectation. And we are now in the parameter space, in this mean parameter space, let's say, such that the expectation is mu alpha. So we have a vector of mean parameters, mu1 till mu d. And we assume that we have d sufficient statistics. So M is always a convex set, and it forms like this. So these points are phi of x. So we can assume that our mu is inside. So any point could be mu. And because it's convex, we can find a collection, just a collection of pairs. For example, this one or this one. So we can approximate by the intersection of all these sets like this. And so we approximate mu. So mu is just this. But this m, so m is like this polytope. But what we want to do is going to approximate m. So the Ising model, Ising mean parameters, what is the probability, what is mu s, what is the probability of x is 1, and the binary one, what is the probability of edge. And so this is the Ising, and these are sufficient statistics. It's a vector, for example, for each of nodes, and then the binary ones. And like this, that we have mu s is the probability of one of xn. For example, for this simple case, that it takes either, so we have two variable x1 and x2 that are connected. So the pair x could be either plus, it could be either 1 or 0, let's say, or minus 1. And x2 could be either 1 or minus 1. So that's M space that I told you, that polytope, is like this. And these are the corners. As I said, the corners are the values and your sufficient statistics. And because we have some constraints, first of all, it should be less than mu I, and also this constraint. Because if we work on this, you will notice that we can obtain these relations. And so this is called forward mapping, because we are no longer working with theta, we are working on mu. So it's a different parametrization. The mapping between the canonical, theta is as the canonical parameter, and mu is called the mean parameter. It's a core challenge that underlies various statistical computations in high-dimensional graphical models. And as I said, the denominator of that exponential family, this cumulant function is hard to compute. But what we are doing is, first of all, we take the derivative and it becomes this. So it becomes a familiar things, expectation of phi of x. And it's a really important property. And we will see why. So we want to say, when does this gradient of A defines a one-to-one mapping, and when does the image of our omega under the mapping is the set. It fully covered the set M. And the gradient mapping is one-to-one if and only if the exponential representation is minimal. And that's a simple proof. But what is important is, in a minimal exponential family, the gradient map is onto the interior of M, polytope M. And so for each mu inside that polytope, so for each mu inside that, there exists some theta, so it's onto theta of mu. There is a map between any mu and theta, And so what is important is that given a function a, that your denominator, you can find the conjugate dual function to that easily, because they are convex, and so this is the conjugate dual of a. Because it's simpler to work with this conjugate dual in most problems in optimization. But it's not dependent on the theta, but now it's dependent on the new parameter. That's why we call it reparametrization. It is dependent on mu. And it is called dual variable. Mu is called a dual variable. And so there is a theorem that says the log partition has this variational representation. And also what is important is this part. You can write that A star to be minus entropy. And we will use this in the next slides. Because you have a form for the conjugate dual of A, which is it's just a negative entropy. Negative entropy of your probability that is hard to find. And so that is negative entropy. We can calculate that. So in the previous slide, you see that this one can be seen here. And we knew that theta, for any mu, there is a one-to-one for theta using the inverse gradient. And in the next lecture, we will continue and think about why these are important.